Hello everyone, welcome to the week 10 problem solving session for deep learning. I am Tanuka from IISc. So in today's session we will be discussing problems about normalization techniques, different types of normalization technique. So to start with, let us briefly revise the different types of normalization techniques that we have talked about in the class. So let's say we have in a batch we are learning our model in mini batch optimization method, or we are using our data in small batches and doing our optimization and adapting the network weights. In that, let's say in one such mini batch there are n number of samples, capital N number of samples in a batch. So like that we have some multiple number of batches, and we are using all those to do mini batch gradient descent or mini batch optimization to minimize our loss function and adapt our network weights. So let's say in a batch there are n number of samples. Let's say we are considering a CNN sort of network. So we can represent it as, let's say I represent each sample by a column here in this diagram. Each sample is a column, so we have n number of columns or n samples. And for each sample, let's say since we are considering CNN for this case, let's say there are C number of channels of the feature map for each sample, and I am representing each channel by a row. So there are C number of rows. So n number of data samples are there. For each data sample, C number of channels are there in the feature map, and each of these cells represent a matrix W by H, which is width cross height of the, if it's the image, so image, or if it is any other 2D matrix, so that is W cross H. So in case of image, your original dimension will be W cross H cross C. So that W cross H we are representing in each cell, and each row is a channel, each column is a data sample. So the basic idea of normalization is, if X is your data point or feature map, anything, then the normalized feature map X hat is basically X minus mu by root over sigma square plus epsilon. This is the standard formula for doing the normalization, where mu is the mean and sigma is the standard deviation, and epsilon is a very small quantity which we add in case sigma is 0. In that case, this formula will lead to division by 0. So that should not happen. That's why we add a small quantity as epsilon to overcome the issue of division by 0. Otherwise, if it is only root over sigma square or root over or only divided by sigma, then if sigma comes as 0, there will be a problem. That's why we are using this small epsilon. Now there are different types of normalization techniques, right? So the difference is how you compute this mean and sigma, for along which axis and what way you are computing this mean and sigma, that only differs from one normalization method to other normalization method. Let's say if we first consider the batch normalization method. In the batch normalization method, what we do is, for each channel we consider the W cross H matrix for all the data samples. So we are considering this one row, complete one row, and we compute the mean and standard deviation value of this, considering all these W cross H values of the n data samples. We compute one mean and one standard deviation for each channel. So for each channel, now you have one mean value, one standard deviation value. When you are going to do this normalization by X minus mu divided by root over sigma square plus epsilon, for each channel of the feature map you use different value of mu and sigma. Rest the same. For different channels only, you are using different values of mu and sigma, and this value you are computing by computing the mean and standard deviation over that channel's feature map, that channel's W cross H matrix over all the data samples. So this is batch normalization, when you are computing the mean and standard deviation over this entire row. Now the next one is layer normalization, right? So in case of layer normalization, what we do is we take one data sample and we consider all channels of that particular data sample, and we compute one mean, one standard deviation. So here you are computing the mean and standard deviation over each column. So for each data sample you have a different value of mu and sigma, and while normalizing that data sample or that data point, you use that value of mu and sigma. This is basically layer normalization. So for n different data samples, you have n different values of mu and sigma, and you compute those mu and sigma by considering all the channels of W cross H matrices of that particular data point. That is called layer normalization. Now the next thing is instance normalization. In case of instance normalization, the idea is you consider one data point and one channel of that data point. Let's say you considered this. So you have considered this particular data point and you have considered this particular channel of that data point. So that matrix, that W cross H matrix you are considering, and you are taking one mu and one sigma value from this matrix. So for each samples, each channel, you have different values of mu and sigma. Each of the n samples, for each sample, each of the C channels have different values of mu and sigma. You are just taking in this diagram one cell to compute one value of mu and sigma. So this is instance normalization. Okay, and the last one is group normalization. So group normalization is somewhere in between layer and instance normalization. In this case, what you do is you take one data sample, let's say this one, and you take a group of channels. Let's say you take this channel and this channel. So you take a group of channels. Now considering the W cross H matrices of each of the channels in one group, you compute one mu and one sigma value. So for this group, for this particular data sample, you have one mu value and one sigma value. For the, if you take another group with the remaining channels, that will give you another mu and sigma value. This you have to do for each of the data points. So for each data points, each group of channel, you have a separate value of mu and sigma. This is basically group normalization. Now how you choose these channels or how many channels will be there in one group, those are like heuristic quantities that depends on your application, how you want to use it. Okay. So in all those cases, actually you are computing mu and sigma in different ways, and you are using this same formula, this particular formula every time to do the normalization, but these values of mu and sigma you are using different. In case of batch normalization, for each channel you have a different mu and sigma value. In case of layer normalization, for each data point you have a different mu and different sigma value. For instance normalization, for each data points, each channel, you have different values. And for group normalization, each data points, each group of channel, you have a different values of mu and sigma that you are going to use to calculate the normalized value. So this is a like brief recapitulation of what are the different types of normalization techniques that we have talked about. Now having said this, let us move on to the questions of today's session. So the first question we have is, what is not a reason for using batch normalization? And the options are prevent overfitting, faster convergence, faster inference time, and prevent covariant shift. So as we all know, which is not a reason for using batch normalization is faster inference time. So when we are doing batch normalization, basically the idea is we have different batches, right? And in each batch you are separately doing the optimization or the gradient descent. You are computing the gradient descent for each of the batches. So it might happen that the batches are such that the data distribution is different from one batch to another. In that case, the decision boundary between the different classes will be different in case of the two batches. So when you go for gradient descent, in one iteration when we are using the first batch, you are trying to learn one decision boundary. In the next you are trying to learn another decision boundary. So there is a dilemma for the network to which way to converge. So this is basically called the covariant shift. So the distribution is shifting from one batch to another. So there is a difference in the distribution. That's why the decision surface or the actual classifier that has to be learned, that is also different from batch to batch. So the network now has to learn this first batch classifier once, then the second batch again for the first batch, and it will keep on doing and finally converge. But there is a kind of confusion. So basically batch normalization is done so that in every batch, instead of having this different distribution, we will make it zero mean unit standard deviation. So that distribution, zero mean unit standard deviation, then also we renormalize it using the gamma and beta parameters. So with that we kind of overcome the differences in the data distribution from batch to batch, and that's what is called the covariant shift. So batch normalization is basically done to prevent that covariant shift. And once you are doing that, since now the decision boundary will not be that much different from batch to batch, the convergence will be faster. So batch normalization indeed helps in faster convergence. Also it is a kind of regularization also. So instead of so ideally what you should do is you should take the mean and standard deviation of the entire training set and you should normalize by that, but you are not doing that. You are actually normalizing by a noisy estimate of the entire training set's mean and standard deviation. So by introducing such kind of noise, you are introducing some form of regularization, and that regularization also helps in preventing overfitting. So batch normalization indeed helps in preventing overfitting, faster convergence, and preventing covariant shift. But it does not help in faster inference time, because inference time, all the layers that were there, that will indeed be there. Along with that, this batch normalization has also to be done. So there is no benefit in terms of faster inference time. But yeah, the rest of the three will be of course achieved. Moving on to the next one. The next problem says a neural network has 3 neurons in a hidden layer. 3 neurons in a hidden layer. Activations of the neurons for 3 samples of a batch are given. Now what will be the value of mean if we use batch normalization in this layer? So basically in this layer you have 3 neurons. 3 neurons in this hidden layer, and you are passing a batch through this layer. That batch has 3 samples. For the first sample, the output of the 3 neurons or the activation values are 1, 2, 3. For the second sample, they are 0, 2, 5, and for the third sample, they are 6, 9, and 2. Now what we want to do is we want to do batch normalization in this layer. So in that case, the question is what will be the value of mean. So in case of batch normalization, we basically compute the mean along the batch dimension over all the samples of the batch. So here there are 3 samples. So we will take the mean across all the 3 samples. So for the first neuron, the 3 activation values are 1, 0, 6. So we will take the mean of these 3 to get the normalized value of the first neuron activation. So that will be 6 plus 1, 7 by 3. That is the normalized activation for the first neuron. For the second one, we have 9, 10, 11, 12, 13, 13 by 3. And for the third neuron, we have 10 by 3. 10 by 3. So we are basically computing the mean over the different data samples, over the activations given by different data samples. So we have 3 different data samples, so we are dividing by 3 and we are just doing this average. So this will be the value of the mean. Okay. I'm sorry, I told this is the normalized activation. No, this is not the normalized activation. This is basically the mean value. Sorry about that terminology. It's not the normalized activation, it's basically the mean value that we are computing. Now we can use this mean value to compute the normalized activation. So this is basically the mean vector that will be used for doing batch normalization. Moving on to the next one. The next one is, how can we prevent underfitting? 4 options are there. Increase the number of data samples, increase the number of features, decrease the number of features, decrease the number of data samples. Okay. So underfitting means your network or your model is not being able to learn the pattern that is present in your training data. Okay. That pattern that you want it to learn, which will be useful for the classification or whatever task you have at hand, that pattern is not getting learned. So that means whatever representation or whatever information you are feeding to the network, that's not sufficient enough for the network to learn that pattern. So if you want to prevent underfitting, you should supply the network with even more information. So one way of doing that can be giving it more richer representation, that is by increasing the number of features. So by increasing the number of features, you are actually giving the network more information that can be helpful for it to learn the pattern in the training data. So to prevent underfitting, we have to increase the number of features. So decreasing the number of features or decreasing the number of data points, that does not work. Increasing the number of data points also does not work much. That actually helps in preventing overfitting. Actually increasing the number of features is the suitable or the appropriate option for preventing underfitting. Problem 4. How do we generally calculate mean and variance during testing? Options are: batch normalization is not required during testing, mean and variance based on test image, estimated mean and variance statistics during training, and none of the above. So the first point I will make clear here is batch normalization is absolutely required during testing. So the point is, so during training you have done the batch normalization. Let's consider the input layer. So you have done the batch normalization on the input layer and you have modified the data distribution somehow, and you have made it some normalized distribution, and you have learned all your weights and biases based on this normalized distribution. Now during testing, if you do not do that same normalization, then your test data distribution will differ from the trained data distribution, and all your weights and biases are learned based on your trained data distribution only. So if your test data distribution now do not match with the trained data distribution, then the weights and biases may not work for this data. So indeed you will have to do batch normalization here to match this test data distribution also to as far as possible with the trained data distribution, or since you cannot ensure that it will be exactly matched, but since whatever operation you have done on the trained data distribution, the same thing you should do on the test data distribution also, because all your weights are learned based on that distribution. So batch normalization is indeed required during testing. Now during testing we can take one sample at a time and we can do the inference on that sample. So from one sample you cannot compute the mean and variance, right? There is no way of computing mean and variance if you just have one data point, because in batch normalization you have to compute the mean and variance over different data samples, which you do not have. So mean and variance based on the test image cannot be a option. The option is estimated mean and variance statistics during training. So during training, the mean and variance statistics that you computed, you actually take a exponentially decaying average of those statistics and you store those values. And during testing, you use those estimated mean and variance statistics during training to normalize your test data. So the correct answer here is estimated mean and variance statistics during training. So while implementing a batch normalization layer, basically you have to save these estimates of mean and variance statistics, which are basically the exponentially decaying average of the means and means and variances of the different batches. These two parameters you have to save, and another the gamma and beta parameters that will be learnt through optimization, those has to be saved. So these four parameters have to be saved for a batch normalization layer while training. Okay. Moving on, the next question is, which one of the following is not an advantage of dropout? Options are regularization, prevent overfitting, improve accuracy, reduce computational cost during testing. So we have to say which one among these four options is not an advantage of dropout. So the correct answer will be reduce computational cost during testing. So what we do in dropout? In dropout, we use dropout mainly during training. So let's say you have a neural network. When you are using dropout in a particular layer, so in each iteration you randomly choose a number of neurons from that layer and drop those from the network. So when you adapt the weights in that particular iteration, you do not adapt the weights connected to those neurons which you have dropped. In the next iteration, again you randomly choose a set of neurons which will be somewhat different from the previous set chosen, and you again drop this, and while doing the optimization you do not adapt these particular weights connected to these dropped neurons. So in each iteration you are randomly dropping a fraction of neurons from your network and you are not adapting the weights connected to that. But in the next iteration, so in one iteration you drop maybe the first 3 neurons, in the next iteration you drop the last 3 neurons, or some random combination of these things. So you keep on dropping out and you keep on learning, but though you drop out, the weights are there. So when you dropped out, that means in that iteration you did not learn the weights connected to that neuron, but the neurons are there. So in the next iteration you will learn it. So when you have completed the entire training, you have learned all the weights, and during testing you will have to pass your data through all these layers, all these neurons. So computational cost will not be reduced at all. what will happen is, since during training you are randomly dropping some portion of the neurons, so the weights learned or the representation learned by each neuron will be kind of independent. So one neuron do not depend on the other to take its decision. Everyone has its own way of doing the task that you have assigned to them. So it introduces some form of regularization and it prevents overfitting. And in cases and when you use this dropout, your the test accuracy or your generalization ability of the network actually increases. So it also helps in improving accuracy. So dropout is basically a regularization technique that prevents overfitting and improves the test accuracy or improves the generalization ability of your network. But since all the weights are there, though you learned a part of it during one iteration, another part during other iteration, but eventually you learned all the weights, and during testing you will have to use all the weights. There is no like effect of dropout during testing. So the computational cost during testing will not be reduced. Okay. Now, having said that, the next question is, what is the main advantage of layer normalization over batch normalization? Is it faster convergence, lesser computation, useful in recurrent neural network, or none of these? So as you already know, the main advantage of layer normalization over batch normalization is it is useful in recurrent neural networks. So in case any of you do not know what a recurrent neural network is, so recurrent neural network is basically used to learn temporal dynamics in the data or temporal relation in the data. It is basically like in the neural network you are introducing a kind of cyclic computation. So the output from current time instant can be used to affect the input of the next time instance. Like that you can do a recurrence operation. Recurrent operation can be performed, and that actually helps in learning the temporal relation in the data. So like one time step you got the output, you use that time steps output to affect the input of the next time step, and you again compute the next time steps output. So in that output you have the information of the first and second both. So in this way you are kind of learning the temporal relation or the temporal dynamics of the data. For that recurrent neural network is useful, and the main advantage of layer normalization is it is useful in recurrent neural networks over batch normalization. So actually for batch normalization you need the entire batch of data, then only you can compute the mean and variance. But in case of layer normalization you need only that sample to compute. That's why it is useful. Layer normalization is useful in recurrent neural network, but batch normalization is not that useful. So that's the main advantage of layer normalization over batch normalization. Next problem. While training a neural network for image recognition task, we plot the graph of training error and validation error. So in this plot, the lower curve is basically the training error and the upper curve is the validation error. Then which is the best for early stopping? Which point? We have 4 points marked A, B, C and D. Which point among these is the best suited for early stopping? So in early stopping what we do is, early stopping is also a regularization technique which is done to prevent overfitting to the training data. So what happens is, when you keep on learning your model or keep on adapting your weights, over iterations, your training loss keeps on reducing. But after some, your training loss keeps on reducing, and also your validation loss also in the beginning reduces. But after some point it might happen that training loss keeps on reducing, but validation loss starts to increase. That means at that point, though your model is performing better on the training data, it is not performing better on the validation data. That means it is learning too much details of your training data. So it is getting overfitted to your training data, so that it is not being able to generalize to the validation set. So at this point it has started overfitting. So we should stop our training at that point where the validation loss starts increasing. So here C is basically the point where you have got the best validation error. After that your validation error starts increasing. So that is basically the point where you should stop your training so that it does not overfit to the training data. So this is the point where we will do early stopping. This is the best suitable position to do that. So here if some of you might have doubts about this training, validation and test sets, so I'll explain it quickly once. So when you train a neural network with some data set, we basically have three partitions of the data set: training partition, validation partition and test partition. The training partition is basically used to learn the weight values of the network, to do the gradient descent and to adapt the weights. Training data is used for that. Now in each iteration, once you adapt the weights, or maybe after a few iterations, you should test your network's performance on a validation data. For example, let's say you want to do this early stopping. So you need to know the performance on the validation data. Like that validation data is actually some unseen data which is outside your trained data. So that basically gives you some estimate of how your network will perform on some unseen data, or how is your network's generalization ability. For that you use the validation set. You compute the performance on the validation set, and based on this validation set's performance, you let's say decide where to stop, early stopping, where to do. Or maybe if you have some other types of networks, or you are doing some, let's say, hyperparameter tuning. So you use different hyperparameter settings and you train your network and you test it with your validation set. And depending on the validation set's performance, you choose which hyperparameter setting actually to be used. Now when you finally have this model, let's say this chosen hyperparameter based model, there your training data has of course been used to train the weights. Also your validation data information has been used, because based on that data set's performance you have chosen which particular hyperparameter settings to use. So you have already used your information from the validation data. So in some way your validation data was also used to build this network. Now when you actually go for practical deployment, that will be some unknown data set outside this train and validation data, and you have to actually perform well on that data set. Now to estimate that performance, we should have the last test partition, which is unseen for this both train and validation data. So we need both validation and test set, because you have already used the validation data information in, let's say, choosing the hyperparameter, or in, let's say, doing the early stopping. So that validation data is no more unseen to the model. So the performance on this data set does not give you the actual estimate of the performance on an unknown data set. For that we need a third test data set, on which whatever best model we have designed, we will use that model on that unseen test data, and that performance gives us actually the generalization performance of our model on any unseen data that will be encountered in practical scenario. Okay, that's the basic idea of using train, validation and test set. Now let us move on to the next problem. Next problem asks, which among the following is not a data augmentation technique? The options are random horizontal and vertical flip of image, random shuffle of all the pixels of an image, random color jittering. All the above are data augmentation techniques. So random horizontal and vertical flip of image are of course data augmentation techniques. Random shuffle of all the pixels of an image is not a data augmentation technique. Random color jittering is a data augmentation technique. So the answer to this question is random shuffle all the pixels of an image. That is not a data augmentation technique. This is because let's say you have some image, let's say you are doing face recognition, you have the image of a face. If you randomly shuffle the pixels of an image, then the spatial correlations of different pixels are completely lost. Now your nose goes to the position of your eye goes to the position of your mouth, and the face is completely distorted. So now if you put that kind of a distorted image to the network, it will not be able to learn anything. So we should not do any kind of data augmentation that completely distorts or that completely demolishes the pattern that is there in the data. So random shuffle of the pixels of an image is not a data augmentation technique. Next problem is, which of the following is true about model capacity? Where model capacity means the ability of neural network to approximate complex functions. The options are, as number of hidden layers increase, model capacity increases. As dropout ratio increase, model capacity increases. As learning rate increases, model capacity increases, and none of these. So we want to see which is true among these options about the model capacity. So as is clear, the first option is the correct option. As the number of hidden layers increase, model capacity increases. So as you increase the number of hidden layers, you are introducing more neurons in your network, you are introducing more non-linearity in your network. So you are giving the network more weights that it can adapt, more non-linearities that it can fit to actually approximate the function that it has to model, right? So you are giving it more flexibility to approximate that complex function. So as you increase the hidden layers or number of neurons in the layers, you actually give it the freedom to approximate more complex functions, or in turn you increase the model capacity. Dropout ratio actually do not have any effect on this, because dropout ratio is just a regularization technique where you are randomly dropping some portion of the neurons and learning the weights of the rest, again dropping some other portion and learning the weights of the rest. So the total number of weights that are there, non-linearities that are there, that's the same. So there is no more flexibility added to the network by doing this dropout. It's just a regularization technique. It helps in preventing overfitting, but it do not help in increasing the capacity of the model. The learning rate also do not help in this. Learning rate basically helps in faster convergence. It actually is the step that you take during gradient descent that is determined by this learning rate. If you have too small learning rate, you will take very small steps towards the minima. So your time to converge will be higher. But again, if you make your learning rate too high, maybe you will reach quickly near the minima, but you then cross the minima and go to the other side. Again from the other side you cross and come to the previous side, and you keep on oscillating around your minima. That can happen. So you have to adjust your learning rate such that you reach the minima, and also it is in a reasonable time. You do not make it too small learning rate so that it takes eternity to reach the minima. So these do not help in model capacity in any way, only the number of hidden layers, if you increase, that increases the model capacity. Okay. Moving on to problem 10. Batch normalization is helpful because it normalizes all the input before sending it to the next layer. It returns back the normalized mean and standard deviation of weights. It is a very efficient back propagation technique, and none of these. So, as is the definition of batch normalization, it normalizes all input before sending it to the next layer. That's why it is helpful. That's the definition of batch normalization. I hope that is clear to everyone. Okay. Now, as we have done these problems, next we will also discuss the assignment for week 10. Since the solutions are already out, we will discuss those solutions to, if anyone has any doubts, that can get cleared. So the first question that was there is this one. In case of group normalization, if group number equal to 1, group normalization behaves like batch normalization, layer normalization, instance normalization, none of the above. So here your group number is 1, so you have only one group. So if you have only one group, all your channels should belong to that group itself. So as we said earlier, in case of group normalization, let's say this was our representation. This is the axis representing data samples, and this is the axis representing the channels. Now we said that for group normalization, we choose one data sample and we choose a group of channels for that data sample, and we compute the mean and standard deviation from those channels belonging to one group. So now your group number is 1, you have only one group. So if you have only one group, all your channels should belong to that group. So the entire data sample, all channels of that data sample are belonging to your one group, and you are computing the mean and standard deviation over that. So that means you are basically computing the mean and standard deviation over all channels of one data point. So for each data point separately, you take all channels and you compute one mean and standard deviation. So that is what basically is layer normalization. So if group number is equal to 1, group normalization behaves like layer normalization. So the correct option is layer normalization. Now on the other extreme, you have if group number equal to number of channels, then what is the case? So if your group number is equal to number of channels, then in each group you have just one channel. So in each group, let's say you have just this channel in one group, just the other channel in one group, and you will just compute the mean and standard deviation over one channel. So this is basically, as we explained at the beginning of today's session, this is basically instance normalization. So the next question's answer is instance normalization. Now, next one. What is the use of learnable parameters in batch normalization layer? Calculate mean and variances, perform normalization, renormalize the activations. No learnable parameter is present. So the use of learnable parameters in batch normalization layer is renormalize the activations. So the learnable parameters are basically gamma and beta, and you do a gamma x hat plus beta operation to renormalize the activations. After making it 0 mean unit standard deviation, you make it beta mean gamma square standard deviation, like that of a distribution. This actually helps in maintaining the class identity of different data samples. So these are the learnable parameters, and their uses are to renormalize the activation so that not all data points, all classes collapse to 0 mean unit standard deviation. There should be differentiation between different classes. So, that class identity of the data points has to be maintained. That is maintained by using these two parameters, gamma and beta. So, it helps in renormalizing the activations. Moving on to the next one, which of the following is not a procedure to prevent overfitting? Which is not a procedure? Okay. Reduce feature size. So, in case your model is overfitting, that means it is learning too much details of your input data or your training data. If there are some noise, that also is getting learned. So, too much information is being captured from your training data. So, indeed, if you reduce your feature size, that will provide the network with lesser information about your training data. So, that can actually help in reducing feature size, that can help in preventing overfitting. So, reducing feature size will give your model lesser information about your training data. So, it will eventually prevent overfitting. Dropout and early stopping, as we discussed, are some regularization techniques, and these indeed help in preventing overfitting. So, dropout basically learns the weights so that it drops out. So, it do not allow the weights to learn too much details. In case of early stopping, we stop when the model starts overfitting. When its generalization ability starts reducing, we stop the learning. So, these are regularization techniques that help in preventing overfitting. The last option, increase training iteration, that does not help in preventing overfitting, because if you keep on increasing the training iteration, then the weights and biases are getting even more fitted to the training data. So, it actually leads towards overfitting, does not prevent it. So, which is not a procedure to prevent overfitting will be increased training iterations. This is not a procedure to prevent overfitting. Now, the next one, an autoencoder with 5 hidden layers has 10,004 number of parameters. If we use a dropout in each layer with 50% drop rate, what will be the number of parameters of that autoencoder? So, originally the number of parameters are 10,004. Now, in each layer we are doing dropout with 50% drop rate. So, what will be the number of parameters of the autoencoder? Obviously, the number of parameters will not change, it will remain 10,004 only. So, by dropout, we are not actually changing the number of parameters. This is a process of how you learn those parameters. So, in one iteration, you are learning a part of those parameters. In the next iteration, you are learning some other part of the parameters. And you keep on doing this, but eventually you learn all those parameters, and when you go for testing, you have to use all these parameters to decide on your test sample. So, your test sample has to pass through the entire network with this 10,004 number of parameters. So, the number of parameters indeed remains the same, the only thing is how you learn those parameters. So, in each iteration you are not learning all 10,004 parameters, because you are dropping out some of the parameters, but eventually at the end of all the epochs and iterations, you have learned all the 10,004 parameters and all are there. So, the answer is 10,004. Next, suppose you have used a batch normalization layer after a convolution block. After that, you train the model using any standard data set. Now, will the extracted feature distribution after batch normalization layer have 0 mean and unit variance if you feed any input image? Of course, the correct option is you can't say whether it will be 0 mean unit variance or not. because the batch normalization renormalizes the features using trainable parameters. So after training, what will happen, that we do not know. After training, what will happen, whether it will remain 0 mean unit variance when we give any input image or not, that we do not know. So the correct option is can't say, because the batch normalization renormalizes the features using trainable parameters. So after training, it may or may not be the 0 mean and unit variance distribution. This is the last question for today's session. Which one of the following regularization methods induces sparsity among the trained weights? L1, L2, both or none? So as you know, the correct option is L1 regularization. So if your task related loss is, let's say, J of W, where W are the weights. So in case of L1 regularization, you add the regularization term as lambda times the L1 norm of W. So basically the sum of absolute values of different elements of the W vector. In case of L2 normalization, you put the regularization term as lambda times square of L2 norm of W, and you try to minimize this cost function in each case. So in both the cases, if you minimize this, the values of the different elements of the W vector will become smaller. Both of these will try to make the values smaller. But in case of L1 norm, since you are trying to make the absolute value, some of the absolute values you are trying to reduce, it actually helps in making many elements zeros, thereby inducing sparsity. But in case of L2 regularization, it reduces the values, it makes each element having small value, but it do not necessarily lead it to 0. So it do not induce sparsity, it actually reduces the values, it keeps the all values of the W vector to very small number, but it do not make them exactly zeros, or it do not induce sparsity. Whereas in case of L1, where you are reducing the sum of absolute values, there you make some of those zeros and you induce sparsity in the network. Okay. So L1 regularization actually helps in inducing sparsity among the trained weights. So this was the problems that I planned for today's session. I hope the answers are clear to everyone. If not, you can post your questions in the discussion forum. So okay, now thank you guys. We will meet again in the next week with the next set of problems. Thank you everyone.